out of your textbook, where we have a square thread power screw that has a major diameter of 32 millimeter and a pitch of 4 millimeters with double threads. What would the double thread do? When I have a single thread, every time I go through one full rotation, the screw would advance a distance that is equal to the pitch. In other words, the lead is equal to the pitch. If I have a double thread, that would mean with every one turn, I'm going to advance twice the pitch. Or in other words, the lead is going to be equal to 2p. And this is going to be used in an application similar to figure 8.4, where I have a friction coefficient between the threads as well as between the collar and the load that is equal to 0.08. The diameter we're going to be using for the collar is 40 millimeter. And the force that we are going to support is 6.4 kilonewton per screw. We are asked to find the thread depth, the thread width, the pitch diameter, the minor diameter, and the lead. We also want to find the torque required to raise and lower the load, efficiency during lifting the load, the body stresses, torsional and compressive, bearing stress, thread bending stress, then determine the von Mises stress at the root of the thread, as well as the maximum shear stress at the root of the thread. Okay. So this is a good example that helps us put everything that we have learned together. So let's start working on this example together. So for part A, we are looking at a square thread. This is my minor diameter, dr. This would be my major diameter, d. And this is the pitch distance between threads. The height of each thread is p over 2, and the width of the thread is also p over 2. So the first thing we're looking at, the thread depth. So the depth is equal to P over 2 is equal to 4 divided by 2, which is 2 millimeter. The width is also P over 2, which is equal to 2 millimeters. The major diameter D is given as 32 millimeters. The minor diameter dr would be equal to 32 minus p over 2 on that end and p over 2 on the other end, so minus p. which is equal to 28 millimeter. The pitch diameter is going to be the same as the mid-range diameter. Remember, the pitch diameter is a theoretical diameter where cutting through the thread and the gap would be the same, right? So I can see here that the pitch diameter in this case is equal to dm is equal to d plus dr over 2. So that would be 32 plus 28 over 2, which is equal to 30 millimeter. So this takes care of, oh, sorry, I didn't do the lead. The last thing is asked for here is to find the lead. The lead L is equal to N times P, where N in this case is going to be a 2 because it's double threaded, multiplied by the pitch, which is given as 4. So I have here the lead distance is 8 millimeter. Next, we want to find TR and TL. So TR is equal to F dm over 2 multiplied by L plus pi F dm divided by pi dm minus FL. Plus, because we have a collar, I get F times FC DC divided by 2. Plug in the numbers. For F, I have 6.4. So we're going to leave this in kilonewton times dm, which is 30, divided by 2, multiplied by L is 8 plus pi times the friction coefficient. I have a 0.08 multiplied by the mean diameter, which is 30, divided by pi multiplied by the mean diameter, which is 30, minus friction coefficient here is 0.08 multiplied by the lead, which is 8 millimeter, plus 6.4 times 0.08. The diameter of the collar is given as 40 millimeter. So times 40 divided by 2. When I do my numbers, I get here a 15.94 plus an additional 10.24 from the collar friction. I add these numbers and I get 26.18. And these are because we used millimeter and kilonewton. So this would be in Newton meter. So this is the torque that is required to raise the load. The torque that is required to lower would be F dm over 2 times pi F dm minus L divided by pi dm plus FL. And I still get the friction from the collar, F FC DC over 2. This is equal to 6.4 times 30 divided by 2 multiplied by pi 0.08 times 30 minus 8 divided by pi times 30 plus 0.08 times 8 plus the force F, which is 6.4 times 0.08, same as before, times 40 divided by 2. The torque to lower, I get here a negative 0.466, but I still have the friction from the collar, which is the 10.24, or the torque that is required to resist the friction from the collar. This gives me a 9.77 Newton meter. Of course, as expected, the torque to lower is much smaller than that to raise the load. Okay. Next, we go to finding the efficiency during lifting. Finding the efficiency during lifting. So C is the efficiency, E, which is equal to FL divided by 2 pi TR. This is equal to 6.4 times 8 divided by 2 pi multiplied by TR, which is 26.18. When I do the math, I get a 0.311, which is less than 1 as we expect. Next, part D, we want to find the body stresses, torsional and compressive. So for D, we're looking at body stresses. So we get the tau from the torque, and this will be equal to 16 TR divided by pi dr cubed. This is equal to 16, and the torque is 26.18. So I got here 26.18 Newton meter, right? So if we want to go to millimeter, I'm going to have to multiply by 10 cubed, because for the diameter, I'm using millimeter. So dr is 28 cubed, right? So when I do my numbers, I get here 6.07 megapascal. So it is times 10 to the power 6. No, it is the kilonewton. Yes, megapascal. Okay, next is the axial nominal stress, sigma. This is equal to N over A, or is equal to minus 4F divided by pi dr squared. This is equal to minus 4 times 6.4 times 10 to the power 3 divided by pi 28 squared, which is equal to minus 10.39 megapascal. So this takes care of part D. And next, we're going to go to E, where we are going to find the bearing stress, and we are going to use 0.38F for the maximum, right? So I'm going to get here this sigma B is 2 times 0.38F divided by pi dm. For mt, I'm going to put a 1 divided by the pitch. This is equal to, and of course, the bearing stress, I'm going to put a negative sign. So I have a minus 2 times 0.38 multiplied by F, which is 6.4, times 10 to the power 3 divided by pi divided by dm, which is 30, divided by 1 divided by 4. Do the numbers, I get a minus 12.9 megapascal. Next, we go to finding the thread bending stress at the root of the thread. So here F, we have this sigma bending is equal to 6 multiplied by 0.38 F divided by pi dr nt. I'm going to use a 1 multiplied by p. This is equal to 6 times 0.38 multiplied by 64 times 10 to the power 3 divided by pi dr is 28. I have my 1 and the pitch is 4. When I do the numbers, I get sigma b equal to 41.5 megapascal. Next, we want to determine the von Mises stress at the root of the thread. I want to label these stresses according to the directions. So this tau was acting on the y plane in the z direction. This sigma body stress was acting in the y direction. And this bearing, this bending stress is acting in the x direction. So I can call this a sigma x. So this is going to be important when I apply my von Mises equation. Sigma prime is equal to 1 over the square root of 2. And I have sigma x minus sigma y squared plus sigma y minus sigma z squared plus sigma z minus sigma x squared plus 6 times tau xy squared plus tau y z squared plus tau z x squared, and we take the square root of this quantity. This is equal to 1 over the square root of 2, and I have here for sigma x I have 41.5 minus sigma y, which is 10.39. This is squared plus sigma y, which is minus 10.39, minus sigma z, which is a 0, squared, plus sigma z minus sigma x. I have here a 0 minus for sigma x. I have a 41.5 squared plus 6, and the only component I have here is a tau yz of minus 10.39, I'm sorry, 6.07 squared. Close the bracket and we take the square root. When we do the numbers here, I should get a sigma prime that is equal to 48.7 megapascal. The last thing that we have to find here to determine the maximum shear stress at the root of the thread. Okay. Now, if I am using the ductile energy theory, I would take the yield strength divided by sigma prime to find a design factor. Right? Maximum shear can use if we're using the MSS theory. So for part H here, finding the maximum shear stress, I am going to look at, or I'm going to write down here, the stresses. So we have a sigma x that is equal to 41.5 megapascal. I have a sigma y that is equal to minus 10.39 megapascal, and I have a tau yz that is equal to 6.07 megapascal. All the others, my sigma z is a 0, my tau xy is a 0, and my tau xz is a 0. So these are the stresses that we just calculated. In order to find the maximum shear stress, we would like to find, or we need to find, the principal stresses, sigma 1, sigma 2, and sigma 3. So these are the principal stresses. Because the maximum shear stress, tau max, is equal to sigma 1 minus sigma 3 divided by 2. So having observed that tau x is a 0, that tells us that sigma x is a principal stress. So next, in the YZ plane, we want to find the two additional principal stresses. So we're going to find major and minor principal stresses so I'm going to use the equation sigma y plus sigma z over 2 plus or minus the square root of sigma y minus sigma z over 2 squared plus tau yz squared. So when I plug my number in this equation, I get here sigma y plus sigma z. Sigma z is a 0. So sigma y is a minus 10.39 over 2 plus or minus the square root of. Again, I have here minus 10.39 over 2 squared plus tau yz squared. And for tau yz, I have a 6.07 squared. When I do my numbers, I get here, this is equal to a 2.79 and a minus 13.18 megapascals. Now, clearly, if sigma s is a principal stress and is equal to 41.5 megapascal, I have 41.5, I have a 2.7, I have a minus 13.18. So this is sigma 1, sigma 2, and sigma 3. Because sigma 1 is greater than sigma 2, and sigma 2 is greater than sigma 3. So my tau max is going to be equal to 41.5 minus 13.18 divided by 2. Which is equal to 27.3 megapascal. Now, I also want to bring your attention that you can plot a Mohr circle to represent these 3 circles for the 3 plane, and I know we're running out of time here. So my first circle in the XY plane, I have, or if I plot it using the principal stresses, I can use the 41.5, I can use the 2.79 and the minus 13.18 to plot 3 more circles. And this would be my tau max for the largest circle. Okay. With this, you should be able to complete homework 1 over the weekend, and I'll see you all on Tuesday. Thank you.